In part 1 of this video, I looked at our growing knowledge of the universe and how humans became aware of its scale in time and space. Now I want to explain what that knowledge tells us about how our universe unfolded, how the stars and galaxies formed, and how the Earth was created, not by magic, but by physical processes we know and understand. Our universe, which may be one of several in time and space, started with a huge explosion of energy and matter called the Big Bang. Neutrons, protons, and electrons rode in the wake of an expansion of time and space itself. After 380,000 years, the universe had cooled enough for these particles to come together to form the first atoms. Nearly 3/4 of them were simple hydrogen, just one proton and one electron. 28% were helium, which has 2 protons, 2 neutrons, and 2 electrons. Cosmologists thought this cloud of matter must have been patchy, denser in some parts than others. Otherwise, the denser parts couldn't have come together later to form stars. Based on the state of our present universe and theoretical models of the Big Bang, they predicted what this patchy early universe would have looked like. Denser clouds are always a few millionths of a degree warmer than the emptier parts of our cosmos, so cosmologists knew that if they could look back 13 billion years, they should be able to see the heat imprint of these early clouds of particles. They'd have to find background temperatures from the universe's furthest reaches. The instrument that achieved this was NASA's Wilkinson Microwave Anisotropy Probe. It spent 2 years collecting data from 13 billion light-years away, which meant it was not only looking deep into space, but also 13 billion years back in time. Then in 2003, the picture was ready, and the world caught its first glimpse of our universe at birth. What you're looking at is a picture of our universe just 380,000 years after it was born, as the first atoms were being formed. It's like seeing the photo of an 80-year-old man just 19 hours after his birth. The red areas are warmer clouds of matter, the blue areas colder and emptier. Hydrogen and helium, protons and neutrons, drifting in a dark cosmos. The Wilkinson probe results were hailed as a scientific breakthrough. They matched the predictions perfectly. Over millions of years, gravitational attraction pulled many of these denser clouds of matter closer together, and the more dense they became, the greater the gravitational attraction. Just as a spinning skater spins faster when she pulls in her outstretched arms, each swirling cloud began to spin, until they became tight balls of rotating gas. Inside each ball of gas, the pressure increased. Whenever a gas is compressed, it heats up. So hydrogen atoms in the center of the cloud started vibrating faster and faster until they were crashing into each other at such high speed they began to fuse to form helium. Each nuclear fusion reaction is accompanied by the release of energy. The energy makes other hydrogen atoms vibrate even faster, fusing more of them, releasing more energy that fuses more atoms, and in a split second, a chain reaction. Like trillions of hydrogen bombs exploding at once, the ball of gas ignites. The first stars illuminate the cosmos. Early swarms of stars were also drawn together by gravitation, forming galaxies. The first stars burned for billions of years, powered by fusion. But a star has only so much hydrogen fuel. As the energy is used up, the star begins to collapse, pulling the gas ball tighter. Pressure and temperature increase until they're high enough for helium atoms to crash together and fuse. This makes heavier atoms, like carbon and then oxygen. With higher temperatures and pressures, even these atoms fuse until the star becomes a white-hot factory. The energy from these reactions is far greater than the fusion of hydrogen. Finally, the temperature and pressure are so high that the star explodes, spewing its contents into space. Often the shock waves throw these heavier elements against clouds of hydrogen and helium that have been dormant in space for billions of years. This cloud hadn't been dense enough to pull together under gravitation, but the sudden jolt from the exploded star stirs it. Now gravitation starts to pull the denser areas closer together. The life cycle of a star begins again. Only this time, things are different. This time, the cloud of gas is laden with heavier elements. Thanks to spectroscopy, explained in part 1 of this video, we can measure the proportion of the different elements in stars and in our own sun. Because stars have been forming since our universe began, we can see them in all their different stages of development, from their inception to birth, maturity, old age, and death. So we know the rate at which hydrogen and helium fuse. The proportion of the two elements tells us the age of the star. Our sun is about halfway through its life cycle, which makes it about 5 billion years old. So 5 billion years ago, a nondescript cloud of gas must have come together in this way and formed a medium-sized, rather nondescript star on the edge of a very ordinary spiral galaxy. As it formed, the heavier elements in the cloud created rings of dust in orbit. Over time, these came together under gravitational attraction to make tiny rocks, then larger rocks, a process known as accretion. This isn't an extraordinary process. In our tiny corner of the universe alone, cosmologists have detected hundreds of planets, so there could be billions of them in just our galaxy. Some would be too close to a star, and water would boil away in the intense heat. Others would be too far, and water would freeze. But for any planet in an orbit between those two extremes, water would be liquid, just like on Earth. Within a few 100 million years, accretion had created a huge ball of rock that would become our planet. At first it was molten because of the energy of millions of collisions. Then the molten ball began to cool, and a hardened crust formed over it. A few million years after it formed, the Earth was cool enough for water to condense, and over the next billion years, chemical reactions created replicating molecules that would one day evolve into simple cells. In the two parts of this video, we've seen how our universe, our sun, and eventually our planet formed over a period of 13.7 billion years, without any need for invisible beings. So we know the universe wasn't made in 6 days, and of course we know it's a lot more than 6,500 years old. If you want to believe in a recent mythical creation, then you've missed out on a lot of the incredible advances in knowledge over the last 300 years. You've also missed out on something that would have astonished the 4,000 generations of humans who preceded us, and who were so curious about the creation of our world that they had to invent gods and spirits to explain it. They would never have dreamed that one day we'd have the technology to look back in time, nearly 14 billion years, and take a snapshot of the birth of our universe.